Let's take a look at this problem. It's number 12 in section 3.8 on implicit differentiation. A little different than some of the others maybe, but it has two functions, x and y, that are functions of the independent variable t. So x is a function of t, y is a function of t. And we're to express the derivative of y with respect to t, right, dy dt, in terms of the derivative of x with respect to t. Again, since x and y are not constants with respect to t, they're functions of t, we have their derivatives here. Okay, and the equation that you are given that relates the variables x and y looks something like this. And basically, the problem will be different by the number here and the number here, but essentially same process. Okay, so how do we begin? We take the derivative with respect to t of both sides of the equation, right? Derivative with respect to t of both sides of the equation. This side is easy, right? What's the derivative with respect to t of 4? 4 is a constant. Derivative of 4 is 0, so that's easy. Over here, notice we have 5 times x times y, right? 5 is a constant multiple, so I can pull that out. And then I have x times y. What rule do I have to use when I have a product and I'm finding the derivative? Well, the derivative of the product requires the product rule, right? And so I need to use the product rule on this. I'm going to pull the 5 out here. I take the derivative of x with respect to t, right? What is that? It's dx dt, right? That's the derivative of x with respect to t. As we'll see later, that's the rate of change of x with respect to t. Times the function y, plus, and then x times the derivative of this function y with respect to t, dy dt. That's the product rule, okay? Now, at this point, we need to solve, remember, we need to solve for dy dt in terms of dx dt. So I want to isolate the dy dt by itself. First of all, note that I have 5 times all this stuff in the parentheses we just found is equal to 0. Well, 5 times something is 0. This something has to be 0. Or if you just want to think about it in terms of this equation, divide both sides of this equation by 5. You get this right here, okay? Now, what do I want to do? I want to get the dy dt by itself. So I'm going to subtract this, the dx dt times y, or as I'm going to write it, y times dx dt. So if I subtract y times dx dt, right, it comes out over here, 0 minus that is this. And then to solve for dy dt, what do I have? X times this, I need to divide by x. If I divide by x, I get negative y divided by x times dx dt. I think in the example, the box, this is what you're entering in the box, right? And this is the dx dt. Okay, so this is going to be real important because we are going to be applying this type of implicit differentiation to what we call related rates problems. That's where we have 2 or more functions like we do here that are a function of t. And here, think about t as being time, right? So x could be some quantity and y can be some different quantity, and they're changing as time progresses, okay? But they're related in somehow, right? In some way by this equation. And the question is, how are their rates of change related? And that's what we get in this final answer here. And this is going to be very important for us as we apply the derivative when we begin looking at the applications shortly. Okay, hope this helps on this one. And again, if you have other questions for me, please let me know.